Hi everybody. In this short video, I want to introduce some terminology that will be important for the study of oscillations. Oscillations, oscillatory motion, that's just back and forth motion. So I could pull this mass down and it goes back and forth. So that's an example of oscillatory motion. In fact, this particular example is known as simple harmonic motion. And we'll talk about that mathematically in more detail in another video. For now, I just want to introduce some definitions that are general to basically all oscillatory motion. All right, so first we need to have a way to characterize the location of the system. So for this mass spring system, for this particular one, I'm going to follow the bottom of this mass because that's convenient. I could choose this point, I could choose this point and follow that location of the mass. I'm going to choose the bottom. All right, when this system is not moving, not accelerating, this is in equilibrium. This is the x equals 0 position. All right, so if I pull this down, I can pull it down by some amount. It accelerates toward equilibrium and then overshoots and goes to the other side. And notice it goes to the same amount on either side of equilibrium. That amount we call the amplitude of the oscillation. So from here to here is not the amplitude. From here to here, or the absolute value of from here to here. Either of those is the amplitude. Now in this system, the amplitude is slightly decreasing over time. You know, it's getting slightly closer and closer to equilibrium over time. That's because this system is bleeding energy to the environment. If it were not bleeding energy to the environment, the amplitude would not change. It would go back and forth like this forever. So and for real mass spring systems, it's often the case that it will, over reasonably short periods of time, approximately have a constant amplitude. So then in those situations, we can use energy conservation to solve problems, and we'll get to that more in a future class. All right, for now, I just want to go over these basic definitions. So amplitude, given by the symbol capital A, is the maximum distance that the system will go from equilibrium. All right, so if I pulled it down by some amount here and then just let it go without pushing it, it'll go up by that same amount on the other side. That's the amplitude. That's the amplitude. This location is x equals positive a. This location here is x equals negative a. The amplitude itself is a positive number. All right, so much for amplitude. Now, the period. The period, given by the symbol capital T, is the time for one complete oscillation. So like from now to now, so starting here, going down, going all the way up, or starting at the bottom, going all the way up and coming down. So from now to now, or you could even track it in the middle, from now to now. If you're using the middle, you got to be careful because it'll go past the middle on the way up, and it'll go past the middle on the way down. That's only half an oscillation. To be a full cycle of motion, a full oscillation, you've got to track it from location and same direction of velocity. So here to there. All right. So the time for one complete oscillation is known as the period, capital T. Really, the way to measure the period is to measure the time for several oscillations, then divide by the number of oscillations, and then you'll get the time for one oscillation. Great. There's another quantity known as the frequency. The frequency is the number of oscillations per time. So period was time per oscillation. Frequency is oscillation per time. So the frequency and the period are reciprocals of each other. Briefly, let's talk about units. Amplitude has whatever units of length you want to use. Period, units of time, so seconds, minutes, years, whatever. Frequency, well, the units of frequency would be the reciprocal of the units of time. So if you're using seconds for period, then frequency would be in units of reciprocal seconds. It turns out a reciprocal second has a special name, a hertz. Just keep that in mind. I don't think it merits a name of its own, but that's standard. All right. We have one more term, angular frequency, given with the symbol omega. It looks like a W, but this is a Greek lowercase omega. Omega represents the angular frequency. That's 2 pi times the standard frequency. All right, and we'll get into the angular frequency in more detail in a subsequent video. The typical units used for angular frequency are radians per second. Just a brief comment, we could actually just use per second or hertz for angular frequency, but since there's an unit of angular measure in here, the 2 pi, that's 2 pi radians, that's the number of radians in a full circle. That's a unit of angular measure. It doesn't really have units. Radians are non-unit units. But just to keep track of the difference between frequency and angular frequency, when we're talking about angular frequency, as a placeholder, we'll say the units are radians per second. All right, so that's basically it. That's your introduction to oscillations and some of the important terminology. Thank you.